Good afternoon, everyone, and welcome to today's webinar session, Mastering Large Assemblies Part 2, Managing Large Assemblies Efficiently in Solidworks. Thank you all for joining us today. As assemblies become larger and more complex, efficient assembly management plays an important role in maintaining smooth workflows and better performance. In today's session, we'll look at practical ways to optimize large assemblies handling in SolidWorks. At EGS India, we regularly engage with engineering and manufacturing companies to support their SolidWorks requirements across different applications and industries. Through sessions like these, we aim to share useful insights and best practices that users can apply in their day-to-day work. To lead today's session, we have Mr. Anish Kant, Application Engineer at EGS India, a SolidWorks value-added reseller with experience in Dassault system solution across different industries. With multiple certifications in SolidWorks and Dassault System software, he supports customers in efficiently using their engineering tools and workflows. With that, I would now like to hand over the session to Mr. Anish Kant. Thank you.
Good afternoon, everyone. Before we dive in, a quick introduction to EGS India. We are a 140 plus member team working exclusively in engineering software and services. We've served over 1,500 customers across industries like automotive, heavy engineering, consumer products, etc. We are an affiliate of bodies like SA, India, and IMTMA, and we've grown consistently over the last decade. EGS works across three broad areas: engineering services, where we help companies design and validate products; software solutions, where we resell, support, and implement tools like SolidWorks and 3D Experience, etc. And technology training, where we upskill teams on CAD simulation and engineering methodologies. Today's webinar comes from the software solutions team as a technical webinar over here. We'll go into the training agenda, webinar agenda for now. Let me give you a quick map of what we're going to be covering today. I want to start with the single most important idea of this entire session, which is true acceleration comes from reducing the computational tax and not just buying faster hardware. So what this means is the number one mistake that companies make when they feel like the computers are slow or if SolidWorks is slow is buy a new workstation, more RAM, or a faster processor, etc. While the hardware matters, it's often not the root cause. So today's webinar is going to be structured on finding out what the true cause for slowness or issues are when it comes to a large assembly. We'll cover these in 4 phases, where the phase 1 is going to be about SolidWorks, how SolidWorks actually stores files and opens files. Phase 2 is going to be for your problems when it comes to step files and imported geometry. Step 3 is going to be your workflow to clean up these files. So how do we handle these files better? So that's going to be about phase 3. And phase 4 is going to be about how to standardize that across your entire team. All right, we'll start with the first SolidWorks file structure now. So each file in SolidWorks is going to be consistent on 3 different layers. The first layer is going to be your geometrical data, where the shape or your size of the product is going to be determined with respect to your surfaces, extrusion bodies, edges, vertices, etc. So the geometrical data is going to be present as the first layer. The second layer is going to be for your tessellated data or triangular information, where that is what is going to be used into for displaying your model in your display over there, interface over there. So what it happens is every solid body or surface body which is determined in your first layer is going to be converted into 2D triangles in your second layer. That is going to be a tessellated data. Both of that is going to give you the image in your screen. Whereas the third layer of data, that is going to be the parametric definition, where that has your history or features of your design over there. So how the model has been created, what are the features that has gone into it, what are the mates, how it has been positioned in an assembly, etc. So these are the 3 different layers of data present in a SolidWorks file over here. Any SolidWorks file, be it a part or an assembly or a drawing, is going to have these layers inbuilt within them. And the first basic feature that SolidWorks presents you with is you get to choose the amount of data that you bring into your display. So when you open a file or a large assembly over here, you get the options to choose which level of data do you want in your assembly. So there's basically three different opening types present in your SolidWorks environment over here. The first is going to be your resolved mode, where all three layers of data is going to be brought into your assembly or into your system RAM, where it's going to have all the uh, shape level data as well as your display data as well as your history or features that you've used to create the model over here. The second mode is going to be the lightweight mode, where uh, the data level with respect to how we have created it, the features, the mates, etc., is not going to be present until you click on a specific part or a operation over there. So by default, only two layers of data is going to be coming into your lightweight mode. So, and the third one is going to be a large design review, where only the display data is brought into your SolidWorks interface or into your RAM. It does not load your geometry level data or doesn't load your history level data. So for opening or the resources required for opening a file in large design review is going to be really less. So by default, with respect to your task at hand, do you want to completely change the shape or design of your product, or do you just want to add a few components to your assembly, or do you just want to inspect the assembly, have a walkthrough of it? Depending on these tasks, you can decide which opening type that you want to go to. So it can either be a resolved mode, it can either be lightweight mode, can be large design review. But depending on the use at hand, bringing in less amount of data is always better when it comes to working or opening an assembly over here. Next. So what is the conclusion on these open types? The first is going to be never initialize a top level model in a resolved mode. So unless you want to completely change each part level shape and design of it, if you want to edit all the features with respect to the entire assembly, then go for resolved mode, but always go for lightweight or LDR mode over here. When it comes to just checking layouts, or you just want to check interference, or if you just want to slice and see the components inside, always go for LDR mode. So if it's only for a verification point where you want to check if there's any interferences involved, if all the components are in the right position, if all the components are there in the first place, always go for LDR mode over here. This is a large design review. And by doing this, we selectively load geometry where only required over here. So this keeps the system memory clear, and it eliminates continuous data swapping between your storage and your RAM over here. So every time that you save or modify data over here, the when opening it in lightweight or large design review mode, the amount of data that gets transferred between your storage and your RAM reduces by a huge amount. So this is the most biggest benefit when it comes to opening a file over here. By having a small option to just move scale up and down, we get to choose the amount of data that is transferred between your working condition and your saved file over there. This is the conclusion for the phase one. When it comes to phase two, we'll see what it is when it comes to a large assembly. So when it comes to a large assembly, it usually comprises of three different types of files. One is going to be the design components, where the mechanism or the internal components that you designed by yourself. So all of the data present within such files are going to be completely designed by you. So there's not going to be much errors, or there's not going to be much complexity in the nature of the files. By ensuring that you're designing with the right design intent in the first place, and then moving on to error-free mates and error-free constraints in your assembly, we can confirm that there is no risk involved with your design components. So the second one is going to be your structural profiles, where it's structural systems or components that usually make use of the elements and frameworks. So although the size of the components might be very big, they do provide us a clean way of designing those components and designing the structures over there. So even the structural profiles are also not going to be of any risk. The most highest risk is going to be the components that we download or get from our source vendors over there. So components like valves, motors, actuators, bearings, etc. So these type of components is what is going to be causing a lot of issues for you in this particular example over here. So there are a lot of other issues that might come up with the large assembly. So, but we're going to be focusing over here on the bought out hardware components over here. So what usually happens when we download a step file? How do we make it better? So that is what this webinar is going to be about right now. Why are we focusing on imported geometry alone or your step files alone? So the first issue is going to be called as the neutral format trap. So what happens when you have a step file is the files that you get from the vendor or websites, it's mostly going to be in step pages or some non-native SolidWorks file. So all of these formats, they don't usually have the history of how the model has been generated, how the model has been created. So every time a particular file needs to be recalculated or rebuilt, it is going to come up with the entire shape by itself, which is going to be a lot more time consuming and resource consuming over there. Another issue with this is your massive instance duplication. So any imported geometry that you have, for example, like a motor or with respect to your bearings, etc., it's going to be used everywhere in your assembly, in your large assembly. It is not going to be used just once or twice. So the impact of such files is going to be multiplied across your entire assembly. So that is why we mentioned here as the multiplier effect. I'll get into detail in it in a bit. And another problem with common step files or imported files is that it is usually hyper detailed. So for example, let's take a motor. The motor is usually going to have all the brush, the coil, everything detailed to the core in the file present over here. So when it comes to an assembly, since it's a bought out component, we're mostly going to be just buying the component, fixing it in your assembly. So for a manufacturing point of view, the information needed is only going to be your mounting points, and it's going to be just for a visual reference that you have a motor or a water component over there. So for interference detection, etc. For those reasons only, we're going to be having a water components. But having the internal components like coils, etc., shown in your assembly is not a requirement, as it is not going to make it to the drawing sheet also. So when it comes to a manufacturing point of view, we're only going to be designing the brackets and mounting cushions, etc., and not the internal components. So the hyper details present within the assembly is also not going to be required in this case. So that is the example that is shown in the right for you. We have a motor with a coil where only the coil is giving you around 1.5 lakh plus graphics triangle. So like I said, how every component or design they make is going to be split into 2D triangles, which is used for representing it in your graphic interface. So those number of triangles is what is called as a graphics triangle. And in general terms, a higher number of graphics triangle is equal to a lot of resources or time required for displaying, rotating, or moving the component in your work graphic interface over there. So when it comes to this particular example, the internal part that is not required is contributing to 1.5 lakh graphic triangles in one instance. So let's say that I'm using 15 motors across my assembly, then a unnecessary 22.5 lakh graphic triangles are inserted into my top level assembly, which is not required at all. So this is another common, this is one of the common issues when it comes to imported geometry. So we'll see how to handle this, and we'll go in detail into what is the difference between a step file and your SolidWorks file over there. So a native SolidWorks file, it will have a design tree. For example, draw a sketch, extrude it, and then you cut a hole through it. So the software basically knows what is going to be happening in order, and it calculates the geometry in such order. So it makes it easier for the system to understand what is the history on how the design has been made. So it makes it easier for it to calculate it. But for when a step file arrives with no history involved, so it's just the final shape, a collection of static faces and edges, no intelligence behind them. So SolidWorks has to evaluate the entire shape from scratch every single time, rather than following a simple recipe. So instead of just going from one step to another, it has to calculate the entire solid geometry in one go. So that is the biggest problem when it comes to a step file or an imported geometry case over here. There's another default thing that happens when you import a step file or import a non-native CAD file into your SolidWorks network. So that is called the 3D interconnect feature. So the recent versions of SolidWorks use a concept called 3D interconnect. So what this basically does is instead of converting it into a SolidWorks file and keeping it in your assembly or part, it just creates a visual representation of it. So it holds on to the step file or the non-native CAD file in the background and has that reference linked to your visual component that is shown in your interface over there. So what this usually does is every time an assembly is opened or rebuilt, or if you're working on a sub-assembly level, or if you're just adding another component, it triggers a rebuild, and SolidWorks will go and search, track down and search the original step file that you've imported over here. It'll re-verify the link and again calculate the model from scratch. So since it is not an entity of its own, it's just a representation of a step file present in the background. It goes through this entire process of calculating every single face and vertex and edge again to display it in your interface over there. So this is one of the problems with uh, step files or non-native CAD files, where there's a lot of background process involved in your when you insert it in your assembly or part file over here. So that is shown as a difference between the top and bottom images. Once, excuse me. Yeah, sorry about that. And there are a few more issues when it comes to step data as well, since we don't have control over how the design was built or what are the steps involved in making the component. So one example was what we saw, the high triangle counts present in the coil over there, the 1,80,000 component graphics triangle present. Another two issues are with respect to your geometrical issues over here. So your irregular microfaces where tiny extensions of a face are seen regular within step files. Another issue is your open surface gaps. So what happens when you when there are certain geometrical errors with respect to step files is that yeah, sorry about that. So what usually happens with imported geometry is that there are some irregularities or anomalies with your geometry itself. So the first case is going to be your microfaces or slivers where tiny extensions are there going to be present between where your edges meet and your faces coincide with each other. There are chances that there are irregular geometries present in it. Another issue is the open surface gaps, where sometimes your 3D geometry is not entirely complete, and there might be some gaps or some irregularities in your faces present. So these are common issues when it comes to step files. So what usually happens is these step files need to be calculated every time, like I said, because of the 3D interconnect link. And because of that, these open surface gaps and microfaces cost a lot of time to rebuild in your SolidWorks environment over here. So what is the overall cost of such unoptimized step data? So if you're not making any changes to it, your opening time is going to be increasing, your rebuild time is going to be increasing, and there's going to be a lot of graphical triangles that are coming into your top level assembly without any proper intention. So this is the overall issue that has been defined with respect to your step file or imported geometry over here. So how are we going to solve it? So I have a simple 4 to 5 step process for managing these imported files over here. So first one is going to be your isolate your components. So instead of maintaining the link with your existing step file or neutral files over there, we are going to cut the link and save it as a separate part file over here. Excuse me 1 second. So like I said, there's going to be a 4 to 5 step small process to clean up these files over here. The first is going to be your isolating your reference link. So instead of maintaining the links with your existing part file or existing, sorry, step file, we're going to cut the link and save it as a localized file in itself. So a self-sustained file, which does not have any reference to your existing step or non-native cat format files over there. The second is going to be purging your internal details where we're going to identify and delete the internal components. So this can be with a simple delete command, or you can also use commands as defeature or simplify to use your SolidWorks inbuilt commands and remove the internal detail. The third step is going to be your remove external features over here. So when it comes to bolts, axles, etc., there's going to be threads involved with it. Or even sometimes when it comes to step files, there's going to be your cast marks or textures present in your faces. There can be text images or text which is embossed onto your design over there. So all of that is going to cost in your overall top assembly. So we're going to simplify all of that. And the fourth one is going to be how to standardize these and make sure that it doesn't get calculated every single time. So this is the process that we're going to follow. We'll go into it step by step. The first is going to be your isolation. So to isolate the components from the reference links, we're going to use a component called break links. It is you might be able to see it in the image over there. So we'll just right click the top level component and use the command break link. By breaking these links, we'll convert the files into SolidWorks files, SolidWorks native part and assembly files with imported bodies in them. Your reference to your existing non-native CAD files is going to be cut and converted directly into your SolidWorks file over here. So by doing this, we convert it into a self-contained part within the document without any external references. So every time there's going to be a rebuild or rebuild triggered in your assembly, it is not going to go in search of your step file and go through the process of re-verifying the geometry, etc. So this is a mandate when it comes to every non-native CAD file over here, where this break link is supposed to be done irrespective of the use case over here. The next is going to be purging or eliminating your internal details. So like I said, your components that are not going to be required for your top level assembly can be removed by completely deleting the face or body over there, or can also be removed with a simple cut extrude or a boss extrude which overlays geometry on top of the existing feature. We can also use the defeature tool to strip away everything hidden from external view. So for example, in this case, you can see that there are multiple layers to the bearings with the balls inside the bearing also available. So all of these can be deleted or using the defeature tool can be stripped away to make sure that only the outer faces that is required for your assembly is present in it. So by doing this, we reduce the number of graphics triangle present over here, and we also reduce the overall file size and opening time, etc. So all the basically the data present inside the part is going to be reduced by this simple option over here. Your step 3 is going to be your external simplification. So what we're going to do over here is sometimes when it comes to these components, these outer faces might be required when it comes to your assembly, detailing, etc. So over here, we're going to make use of this concept called configurations in SolidWorks, where we configure certain features like a boss extrude, cut extrude, to simplify the geometry present in this. So we create a simplified configuration and create your boss extrude and cut extrudes to simplify the configuration. And on the default configuration, all of these additional features that we've added can be suppressed and kept. So by doing this, we can maintain two different versions of the same geometry within the same file. Depending on the use case, each of this can be selected. So if you're working on the top level assembly where you might be working in a different sub-assembly or you might be working with a different components, in those cases, the simplified configuration can be kept so that it reduces the graphics triangle, the load on the processor and RAM is reduced. So it makes it easier for you to work in your top level over there. When it comes to detailing or when it comes to interference checks, you can switch back to the default configuration where these configuration will have the data required for your detailing or your interference checks over there. So this is how we make use of configurations in our imported file handling methods over here. The another example is going to be your how to remove threads. So in general, threads are usually defined with your callouts in your drawing sheets over there. We're not going to specifically mention the size of cut or the angle of cut, etc. We are just going to denote that with a callout in your drawing sheet. So why have it in your top level assembly over here? So in this case, you can see that there's not much difference between the top component and the lower component visually. Because what I've done over here is used a concept called cosmetic threads. So what this cosmetic threads does is it just adds a small appearance on top of your component to show that there is a thread present to it. You can also define a call out over here, etc. All of this can be called on to your drawing sheet automatically. So instead of having the physical helical cut within your top level assembly, you can have just a representation of it where it is almost zero graphic angle and zero resources required for it. So by either just adding an extrude on top of your thread or by recreating the component with cosmetic thread, you'll be able to save a lot of graphics triangle from entering your top level assembly for one specific instance. But all of this can be multiplied, all of the impact would be multifold when it comes to multiple components being used in your top level assembly over here. Your step 4 is going to be your freeze bar over here. What is a freeze bar? So a lot of people might not be doing this, but a freeze bar feature is basically preventing SolidWorks from recalculating the geometry. So it is basically saying that this design is fixed. You don't have to recalculate it every single time over here. Enabling it, it will be through your options present, the system options in the general tab. There will be an option to enable the freeze bar. By doing this, you'll have the orange color line present right below your part name. By dragging the component below, you'll be able to lock those specific features or bodies present over here. So this is what a freeze bar does. And the benefits of freeze bar would usually be that once you lock all the features present in your assembly or in your part level, the SolidWorks doesn't take time to rebuild or recalculate your geometry over there. So it just makes sure that it is a check for saying that, okay, this geometry doesn't change, so you don't need to calculate it again. So that is what the freeze bar does to a part file. So we saw how to clean up your step or imported files over here. The first is going to be where you break the link, which basically eliminates the background checks or background checks every time you rebuild or recalculate your assembly over here. You're going to remove all the internal details that are hidden from you. So by doing this, it reduces the file complexity, it reduces the graphic triangles coming into top level assembly, it reduces the opening time, etc. For the external features, which might be required in specific situations, we're going to configure them in such a way that we have a simplified configuration for most of our work. And when it comes to the specific purpose, we can switch it to the default configuration over there. And we're also going to be removing threads, etc., and use cosmetic threads as an example to represent threads present in your bolt or axle, etc. And to make sure that all of these do not change and to make sure that SolidWorks does not calculate all of these features again, we're going to make use of the freeze bar present in your SolidWorks environment. By doing this, we complete the process and say that the geometry doesn't change over here. You don't need to recalculate the entire part or assembly over here. So this is what the freeze bar does. So these are the rules that in a simple way are used to optimize your step or imported geometry over here. The next is going to be for one person, this might be fine. So let's say that I'm a part of a design team where there are multiple designers involved. I'm just one of them. Me knowing the process and doing it correctly might not help the entire team. So since it's going to be a large assembly. People are going to be working on sub assemblies with themselves. So how do we standardize this? So to make sure that this has to go through the entire team. So this is where we have something called like a workflow that I'm just presenting it to you now. The first is going to be the quarantine phase. So what we recommend is first dedicate a person or a team who's allowed to download and add your standard component step files, etc., into your design workflow over there. So not everybody gets access to download the files. Only one or two specific people are equipped to download the files over here. Once they download it, they should save it to a separate file, a folder over there, which is not supposed to be used directly into your overall production design. So the next is going to be your sanitation phase, where a designer will open up all of these uh, raw existing files, the original files, and make all the changes. So deleting the internal details, removing the threads, being the link, etc. So all of the 5 steps that I just shown you. So all of that has to be performed in your second phase over here in this. And once all of this is completed, it has to be then moved to a third folder, which is your release phase, where these components that are optimized for your main assembly are maintained in a proper design library. So what is a design library? So design library is basically like a common repository of files where I can where the entire team will have access to. So this can be set up like a shared folder where all the common files are going to be used directly from your design library. So any imported geometry is going to be simplified and put into your design library, and the entire team will be able to drag and drop it from the design library present over here. So the objective is to ensure that every engineer has access only to those simplified components and not just any step file present in the internet over there. So this is the use case of design library in this specific scenario. The option to add a location will be present in your system options again under file locations, where in the drop down, you'll be able to select your design library. By clicking add, we'll be able to add the geometry, add the file location for your design library over here. So how does this design library help speed up work? So as you can see here that it is present right within my SolidWorks environment in the task pane over here, design library. Any components that have been simplified, I can just drag and drop it from my interface itself. I don't need to go search in my Windows Explorer, find where my paths are, etc. All of that is going to be within my SolidWorks environment. From the design library, I can just pick and place, drag and drop my components into my assembly over here. So all of this is standard pre-optimized components. Like I said, the cleaning up work was already been completed by another person. So we'll just make use of those standardized components to make sure that our top level assembly is working smooth and proper. So even there's another issue when it comes to step file and download components is even when I do all of these work, like let's say that all the designers know how to break link, know how to simplify the geometry, they will still be saving it under different names, and all of that will be considered as different parts when it comes to the top level assembly over here. So this creates a lot of problems in your detailing, BOM creation, etc. So when you have a standardized design library present, all of this makes it very easy. So the same component will only have one source in it, and that source will be multiplied across the entire top level assembly, and that again will be reflected in your top level BOM as well, saying that the overall count, we don't have to make any changes to it. It is a proper count over there. So to sum up the entire webinar for now, the first is going to be measure where using the SolidWorks performance evaluation, we'll be able to identify which component or which subassembly contributes to your opening time, which has a lot of graphics triangle involved, etc. So first we'll have to be measuring your overall top level assembly. The next step would be once you measure it, when you find out these components are the root causes, you'll be able to optimize it with the 4-step cleanup that I just showed you. That is the break links, purge, internal components, configure, freeze, etc. So that will be the 4-step cleanup workflow. Once you optimize it, you standardize it with your design library through your entire team over here. So this is the three major steps to a simple way to complete your top level assembly over here and make performance better. So achieving lightning fast assemblies through engineering discipline, not just hardware spec. So comes back to the first point where we started, where it's not just about the hardware. To find out the root cause and solve issues in your SolidWorks assembly, this is the workflow to go to. Thank you so much.